Hello students, welcome to EPG Pathshala. I am Professor B.K. Sen, Chairman Bibliometrics Committee, Department of Science and Technology, New Delhi. Today we are going to dwell on the module Classical Laws of Bibliometrics and the papers Bradford's Law, ZIPF's Law and Lotka's Law. The objectives of today's lecture is to make you know the classical laws of bibliometrics and to make you learn the formulas pertaining to the laws and to make you able to apply the laws in library environment and to educate yourself as to how these laws are verified. Lotka's law. As I have already pointed out that there is a relation between less and more, Lotka's law also deals with the same thing. He found out from his studies that less number of authors contribute more number of publications. You take a list of authors and you find out their publications. You count their publications, then you will find that a very large number of authors have contributed or have written only one book. And if you want to find out the number of authors who have contributed 50 books, their number will be extremely less. So this is the Lotka's law. The law says the number of authors, say Y, making X contribution in a field during a specific period of time is about 1 by x to the power n of those making one contribution each, where n is roughly equals to 2. The value of n, that is not constant. It varies from subject to subject. In some cases, the value of n is less than 2. In some cases, the value of n is greater than 2. So using this particular law, you can find out that if 1600 persons have contributed one paper, then you can find out how many persons might have contributed 2 papers each, how many persons have contributed 3 papers, and so on. Bradford law of scatter. The law is defined as if scientific journals are arranged in order of decreasing productivity of articles on a given subject, they may be divided into a nucleus of periodicals more particularly devoted to the subject and several groups or zones containing the same number of articles as the nucleus, when the number of periodicals in the nucleus and succeeding zones will be as 1:n square. In a situation where the data ideally suits Bradford distribution, the set of journals, say numbering 310, would be divided as 10, 10 into 5 and 10 into 5 into 5. The first 10 journals will belong to the core zone, the next 50 to the allied zone, and the last 250 to the alien zone. The number of papers in each zone will be the same. In reality, we do not get such data that perfectly satisfies the law. In most cases, the data satisfies the law roughly. This slide is a table which shows productivity-wise distribution of periodicals. It has 4 columns. The first column is rank, second column is number of periodicals, third column is number of articles, and the fourth column is cumulative total of articles. Here we find in the first row, that is rank 1, number of periodicals 1, number of articles 93, cumulative total 93. In this way, when we come to the 8th rank, we find that there is 1 periodical and the number of articles is 20 and the cumulative total is 412. It is a continuation of table 1. In this we find the rank number 9, which has 1 periodical, 17 articles, and cumulative total is 429, and the last rank here is 30, and where there is number of periodical is 3, number of articles are 9, and cumulative total is 689. This is showing table 2. Here we find the 9 to 13 position of the table. In table number 1, we got only 9th and thereafter 13th position. Here in this, we have split it into all the positions, this is all the ranks, 9, 10, 11, 12 and 13. And you find that in each case there is only 1 periodical and the number of articles are also in the 9th rank 17, but in the rest of the cases it is 16, and cumulative total of articles, there you find 429, 445, 461, 477 and 493. Now we have already talked about the 10th rank and 445, that is cumulative total. In this table you can see that. Here you find table 3. Here we have shown you the 56th to 60th rank of the table 1. And in table 1 you have not seen the 60th rank. Here you find that in the rank it goes from 56th to 60th, and the number of periodicals, that is from 57 to 60th, is only on 1, and number of articles, they are 57 to 60th, it is only 5, and the cumulative totals of the articles, when it comes to the 60th rank, it is 888. This is slide 14, devoted to distribution of articles in Bradford zones. In Bradford zones, you find 3 zones, 1, 2 and 3, and the number of periodicals in the 3 zones are 10, 50 and 266, and number of articles in the 3 zones are more or less the same, 445, 443 and 444. It relates to the distribution of articles in 3 Bradford zones. The articles here, that is 1, 3, 3, 2, are to be divided into 3 equal parts. Each part should have 444 articles. In most cases, they will not be exactly equal. It is to be seen that the number, I mean the whole number, matches a particular rank. In table 1, 9th rank matches with 429 and 10th rank with 445. As 445 is close to 444, hence the first zone, 10th rank, is selected. In table 1, there is no 10th rank. Table 2 shows 10th rank, how 10th rank is obtained. For the second zone, the next 444 articles are to be taken. This takes us to the cumulative figure 888. From table 1, it is clear that 888 lies between 868, that is 56th rank, and 926, that is 68th rank. Table 3 shows that the figure 888 pertains to 60th rank. From table 1, we find that the figure 1332 belongs to 326th rank. Table 4 depicts the distribution of articles in 3 Bradford zones. From the data given above, we get the value of N as 5. That is, in the first zone there are 10 periodicals, in the second zone there are 50. We divide 50 by 10 and get 5, and this is the Bradford multiplier. Now we multiply this 50 by 5, we get 250, which is close to 267. Thus, the ratio of the periodicals is 10:50 is to 267, which is roughly 1:5 square. Thus, we conclude that the data set follows Bradford's law, and it is called Bradford Bibliograph. For drawing the bibliograph, take y-axis for the number of periodicals and x-axis as the number of articles. The graph may be plotted in a semi-log paper. The computer literates may draw the graph using a computer. In the world, we observe a peculiar phenomena, that is, a less number of objects. They are becoming responsible for more number of events. For example, you will find that less number of cricketers scores more number of runs, or less number of footballers score more number of goals. Similarly, we have seen in Bradford's law, the less number of periodicals, they contribute more number of articles. So, similarly, in less number of diseases, they take away more number of lives. So, in the less and more, there is a beautiful relation, and also we have seen that less number of persons in the world, they hold very much amount of wealth. So this is the world. ZIPF, he studied language. He was interested in linguistics. So obviously, his laws are related to linguistics, and linguistics, he has found out that human beings, they use words which are of shorter length much more. For example, you will find in English language 3-letter words, 4-letter words, they are much more compared to 10-letter, 12-letter or 15-letter words. So basing this, also a law has come out, that is law of least effort. So in English language, as I have said, that you will find more words with shorter length, much more words with shorter length, and very less number of words longer length. So here he found another law where it is with the use of words. There are authors, any author you take, you will find that he is using certain words much more compared to the other words, and this was the basis of ZIPF's law. There is one of his laws which is in your course, and we have discussed this law in the audio session. So in this law, you will be interested to know that authors have got peculiar tendency of using some words much more than other words, and this is governed by a law. For example, in his Gitanjali, Rabindranath used the word Ami much more than any other word. This rank of Ami is 1, and it occurred in Gitanjali about 2000 times. And the second ranking word, that is called Tumi, that occurred about 1000 times. So, rank and frequency, ZIPF found out to be more or less a constant. That is why he laid down this law, that is, the conspicuousness or intensity of an element of language is inversely proportional to its frequency. That is, if the frequency is less, that is 1, 2, 3, and the number of words, that is frequency, is high, then rank and frequency you will find a constant. As I said, that in Gitanjali, the rank of Ami, it is 1 and the frequency is 2000, and second rank is Tumi and the frequency is 1000. So if you take the product, in both the cases it is around 2000, and he has analyzed Ulysses, James Joyce's book called Ulysses, and he has found out beautifully that more or less roughly this law follows. It follows with any author, any language. You can try this, and you will be, even in your writing, if you try with your writing, you will find that this law holds good. It relates to the distribution of articles in 3 Bradford zones. The articles here, that is 1332, are to be divided into 3 equal parts. Each part should have 444 articles. In most cases, they will not be exactly equal. It is to be seen that the number, I mean the whole number, matches a particular rank. In table 1, 9th rank matches with 429 and 10th rank with 445. As 445 is close to 444, hence the first zone, 10th rank, is selected. In table 1, there is no 10th rank. Table 2 shows 10th rank, how 10th rank is obtained. For the second zone, the next 444 articles are to be taken. This takes us to the cumulative figure 888. From table 1, it is clear that 888 lies between 868, that is 56th rank, and 926, that is 68th rank. Table 3 shows that the figure 888 pertains to 68th rank. From table 1, we find that the figure 1332 belongs to 326th rank. Table 4 depicts the distribution of articles in 3 Bradford zones. From here, we are giving the steps one by one. Number 1, take a piece of writing in English containing about 5000 words. The writing can be an article, a short story, a novelette, a part of a novel, even a technical writing. Number 2, scan the selected writing with an optical character recognition software, namely OmniPage Pro. Step number 3, save the file in a suitable software package such as Microsoft Word for Windows. Step 4, check the file with the original to ascertain accuracy. You have to note that if the document is in a digitized form, steps 2 to 4 will not be necessary. Step 5, Consider the textual portion of the writing only and remove the names of the authors, author affiliations, abstract, keywords, alphanumeric expressions like second and F10, alpha-symbolic expressions like AU equal to and ACU equal to, abbreviations such as FDT and ISO, numbers in digits e.g. 324, serial numbering such as A, B, C, etc., formulas, punctuation marks, intra and extra textual references, tables, figures, and appendices. Step 6. In the case of hyphenated words, follow the rules given below. If the hyphen joins a prefix such as coordination, remove the hyphen and consider the word as coordination. In the other cases such as short term, remove the hyphen and consider the combination as two different words. Step 7. Convert the punctuation marks into spaces. Convert all spaces into breaks. Convert all uppercase letters into lowercase letters. Make sure that the file has converted into a pure word file. 11. Sort the file alphabetically and save it as a text file. Step 12. Run the file through a small program that can count the frequencies of word occurrence. The program will take the text file as its input and reproduce the text file with the corresponding frequencies as its output. Step 13. Convert the file into a table with 3 columns, that is, rank, frequency, and rank into frequency. Step 14. Sort the table according to descending frequencies. Step 15. Compute rank into frequency. Step 16. If the product of rank and frequency is found to be more or less the same, the law is verified. This is the equation of ZIPF's law. In this case, X stands for frequency, Y stands for conspicuousness, that is rank, and the law is mathematically expressed as Y versus 1 by X. That is, xy is equal to n, where n is a constant. The definition can be stated in simpler terms as the rank of any word of a language is inversely proportional to the frequency of its usage. The lower the rank, the higher will be the frequency. Relates to the verification of ZIPF's law. It is starts with a manual verification of the law is highly laborious and time consuming. The advent of information technology has given us devices with which we can verify the law without much difficulty. The steps involved in the verification are given below. If the work is done manually, the cards are to be prepared for the entries required for the purpose. Otherwise, the required entries may be entered in a computer in Excel sheet or any other suitable software. Number 3. The cards or entries are to be sorted according to periodicals. This is a hypothetical table. In this table, you find rank from 1 to 10, frequency from 1800 to 180, and in all the cases, the product is 1800. This is a perfect table for ZIPF's law, which usually we never get. ZIPF Bibliograph, taking the data from the table given above, this graph has been drawn, and the graph which you are seeing here, the frequencies are in the x-axis and the rank is in the y-axis, and the curve which you are seeing is the curve of power law distribution. This is showing the distribution of words in James Joyce Ulysses. James Joyce wrote the book Ulysses, and a person, he prepared an index giving all the words as well as their frequencies. So from that we find that in the rank number 10, the frequency was 2653, product was 26530, 20 rank 1311 was the frequency, product was 26220, 30th rank frequency 926, product was 27780, 40th rank frequency 717, product was 28680, 50th rank frequency 556, the product was 27800, 100th rank 285, and the product was 28500. This was, if you see the product, it is seen that more or less they are equal. Now we have described Bradford law of scatter in our audio. Now here we are giving the visual representation of that law in the form of a bibliograph. That is, bibliograph means that it is a graph which is based on bibliometric data. Normally, we get numerous statistical data. In this case also it is statistical data, but they are bibliometric data. That is why it is called bibliograph. We have got Lotka bibliograph, ZIPF bibliograph. Similarly, we have got Bradford bibliograph. Now this graph, how it looks like, you can see it from here. This graph is drawn upwards with the Bradfordian data, and the Bradfordian data we have got in the one side number of periodicals, on the other side we have got the cumulative number of articles. So in the y-axis here we place the number of periodicals or journals, and the x-axis we put the number of articles. Now as the number of articles may go into thousands, and within graph paper, normal graph paper, it becomes very difficult to draw the up to 2000, 3000 or 5000 up to this type of paper. That's why semi-log paper is preferred for this type of bibliograph. So in a semi-log paper, on the y-axis we put the number of periodicals, and in the x-axis we put the number of articles. Even if the number of articles are large, so there is no problem. Now if you see the graph, then you will find initially it is curved. In the middle portion it is a simple straight line, and in the last portion, in the third portion, you will find the curve has drooped down. Now initially it indicates the very the periodicals which is giving a large number of articles. In the middle path we find periodicals which are contributing less number of articles, and in the third they are contributing the least number of articles. So the droop which we find, it is called gross droop. That means if the literature is not complete in a bibliography, then there is a chance that there will be droop in the graph. And uh, for various formulations, we derive some data based on this graph. First, we take Bradford law of scatter, and this law is defined as if scientific journals are arranged in order of decreasing productivity of articles in a given subject, they may be divided into a nucleus of periodicals, more particularly devoted to the subject, and several groups or zones containing the same number of articles as the nucleus, when the number of periodicals in the nucleus and the succeeding zones will be as 1:n square. Now, the periodicals are to be sorted according to the frequencies. The periodical with the highest frequency is to be ranked first, followed by others with descending frequencies. 5. The data is to be tabulated as per the table given above. Special care is to be taken about ranking when there is a tie. Suppose two periodicals occupy 8th rank, then the next rank will be 10th, not 9th. 6. The validity is to be tested according to the formula given above. It gives the equation of Lotka's law. The equation is x to the power n into y is equal to c, where x stands for the number of contributions, y for the number of authors, and c is constant. Lotka found the value of n is roughly 2. It is the verification of Lotka's law, page 1. Step 1. Take an author index of an abstracting or indexing periodical. You can take the whole A to Z index if the number of entries is manageable. Otherwise, you can take part of the index. Step 2. Count the number of entries against each author and write down the number against his name. Let us call this the productivity of the author. If this data is entered into a computer, sorting of the data will be easy. It can also be done manually, recording the data on cards. Step 3. Take about 30 cards. Number each card serially from 1 to 30. Verification of Lotka's law continues. Step 4. In the card number 1, write down the number of authors who have contributed one paper each. Similarly, in card number 2, record the number of authors who have contributed 2 papers. Continue the process till you reach the author who has made maximum number of contributions. Remember, the name of the author is not to be written on the cards. Next step, arrange the cards according to serial number and prepare a 2-column table as given below. Next step, prepare a 2-column table as given below and presenting the data in ascending order. The last step here, taking the value of n as 2, check whether the data fit into Lotka's law. If it does not, you have to try with different values of n. It may be more than 2 or less than 2. By trial and error method, you may arrive at a value that will bring the figures quite close to the actual values. This is a table which is given according to the number of authors contributed, one paper, two papers, three papers, and like that. So the first row indicates that 1024 authors have contributed one paper, 2056 authors have contributed two papers. In this way, there is only one author who has contributed 32 papers. It is Lotka Bibliograph. If you see the graph, immediately you will see that the graph pertains to power law distribution. Dear students, we have just now completed our discussion on three classical laws of bibliometrics. It is time to summarize and find out what we have learned. The three laws that we have learned are Bradford law, ZIPF's law, and Lotka's law. In all these cases, we have also seen that how these laws can be verified with data. And please keep in mind that these laws are scientific laws. In library information science, there are laws which are not scientific, but still they are laws. But in this case, all these laws are scientific laws, and these laws, you can collect the data, you can verify their validity, and also use them. We have not talked about the use of these laws. Say, Bradford's law, it has been used very nicely and very successfully by Eugene Garfield, the founder of Science Citation Index, Journal Citation Reports, and other citation indexes. Now, when he started his Science Citation Index, at that time, there were about 60,000 scientific periodicals in the world. But it was impossible for him to gather all this periodical and to produce that huge volume. Instead, he believed in Bradford's law and he started his work just a little bit more than 600 periodicals. Gradually, of course, as periodicals increased, he also increased his coverage, but he always kept in mind that the Bradford law, that is, the largest number of important articles, significant articles, is published in very less number of journals. So this was his laws, and similarly, the Bradford's law, no, not Bradford's law, it is the ZIPF's law. It has found use in automatic indexing, automatic abstracting, and finding out the most used terms in the particular essays or in particular writings and so on. And Lotka's law helps us to find out the most prolific authors in any particular field.